We've now got two dynamic programming algorithms under our belt. We know how to compute weighted independent sets in path graphs. We also know a dynamic programming solution to the famous knapsack problem. But before we proceed to still more useful and famous dynamic programming algorithms, let's pause for a sanity check. Let's go through a worked example for that dynamic programming algorithm for knapsack, just to make sure that everything is crystal clear. So for reference, let me just rewrite the key points of the knapsack algorithm. So first, we have a 2D array A, and for initialization, just whenever I equals 0, that is, you can't use any items at all. Of course, the optimal solution value is 0, and then I'm just going to rewrite the same recurrence that we had in the previous couple of videos. So you'll recall that in the main loop, when you're considering a given item A and a residual knapsack capacity X, you take the better of two solutions. Either you inherit the solution with I minus 1 and the same residual capacity X, that corresponds to not taking item I, or if you do take item I, you get a credit of V sub I, the value for that item, but the residual capacity drops from X to X minus the weight of item I, and you look up the optimal solution for that smaller subproblem. So for our concrete example, let's just look at a case with 4 items, an initial knapsack capacity capital W equal to 6, and the values and weights of the 4 items as follows. So I'm going to describe the most straightforward implementation of the dynamic programming algorithm for knapsack. We're literally just going to explicitly form the 2D array A. One index for I will range between 0 and n. The other index for X will range between 0 and capital W, the original capacity. There's certainly a lot of optimizations you can apply when filling in these tables. In fact, the future programming assignment will ask you to consider some, but just to make sure the basic algorithm is totally clear, let's just stick with a naive implementation for now. So we begin with the initialization, and setting A0x to be equal to 0 for all x just means we take the leftmost column corresponding to I equals 0, and we fill that in entirely with zeros. Now in a real implementation, there's no reason to explicitly store these zeros. You know they're there, but again, to keep the picture clear, let's just fill in the zeros in the left column. Now we proceed to the main while loop, and recall the outer for loop just increments the index I for the item that we're considering. So the outer for loop is considering each of the columns in turn from left to right. Now for a fixed value of I for a fixed column, in the inner for loop we consider all values of X from 0 to capital W, so that just corresponds in a given column. We're going to fill in the entries from bottom to top. So we begin this double for loop with the second column I equal 1 and at the bottom X equals 0. Now in general, when we fill in one of these table entries, we're going to take the better of two solutions. Either we just inherit the solution from the column to the left in the same row, this corresponds to skipping item I, or we add the value of the current item to the optimal solution that we extract from the column 1 to the left, but also W sub I rows down. So that corresponds to reducing the residual capacity by W sub I. Now, for the early subproblems in a column where you have essentially 0 residual capacity, it's kind of degenerate, right? So if your residual capacity X is actually less than the weight of the current item you're considering, W sub I, you have no choice but to inherit the previous solution. You're actually not allowed to pack the current item I. So concretely, in this example, in the first column, notice the weight of the first item is 4. So that means if X equals 0 or 1 or 2 or 3, we're actually not permitted to choose item 1. We don't have enough residual capacity. So in the first bottommost 4 rows for I equals 0 to 3, we're forced to inherit the solution from the column to the left. So that is the first 4 zeros from the left column get copied over to column with I equals 1. Now, in this outer iteration in the first outer iteration of the for loop, once X reaches 4, now there's actually an interesting decision to make. We have the option of inheriting the 0 immediately to the left, or we can take item 1, therefore getting a value of 3, and then we inherit the solution from A00. And now A00 has a 0, but we're obviously happy to get this value of 3. So that's going to determine the max. We're going to accept V sub I plus A of 0, 0. And that gives us a 3 in this next table entry. By the same reasoning, we're going to fill in the uppermost rows of column 1 with these 3s. We certainly would prefer just taking the item 1, which we're now allowed to do. We have enough residual capacity, as opposed to just inheriting the 0 from the column 1 to the left. So that's how we fill in the column with I equal 1. Moving on to I equal 2. Again, so here notice that item 2 has a weight of 3. So again, the bottommost 3 rows, when x equals 0 or 1 or 2, there's nothing we can do. We don't have the option of picking item number 2. We don't have enough residual capacity. So we just copy the values from column I equal 1 over. Those happen to be zeros. So that gives us 3 zeros to start column 2. Now, when I equals 2 and x equals 3, now we have enough residual capacity to take item 2. And we're certainly much happier to take the value of 2, which is the value of item number 2, as opposed to inheriting the 0, 1 column to the left. So that gives us a 2 in the column I equals 2 with the residual capacity x equal to 3. So perhaps the first truly interesting table entry to fill in is when I equals 2 and x equals 4. Because in this case, we actually have two different non-trivial solutions we have to pick from. So one solution, as usual, we can just copy over the number, which is 1 column to the left. But actually, in this case, there's a 3. There's no longer a 0 to the left. There's a 3 to the left, right? A 1 comma 4 is equal to 3. Our other option is to take the second item, getting us a value of 2, and add that to whatever's in the leftmost column, but shift it down by 3, because 3 is the weight of the second item. And you'll note that A of 1 comma 1 is 0. So picking the current item would just give us 2 plus 0 equals 0. We'd prefer to just inherit the 3 from the column 1 to the left. That is, we'd prefer to skip item 2 so that we get the value from item 1 instead. The upper 2 rows of the column with I equal 2 are filled in with 3's for exactly the same reason. So for example, in the top row, what are our options? Well, we can inherit the 3 that's 1 to the left. If we actually use item number 2, that knocks our residual capacity down to 3, and A of 1 comma 3 equals 0. So again, we'd rather have the 3 than the 2. Moving on to the penultimate column when I equals 3, for the usual reasons, we have to fill in the 2 bottommost rows with a 0. Notice that the weight of the third item equals 2, so we need a residual capacity x equal to 2 before we can actually use it. Now, when x equals 2, we'd much rather have the value of 4 for the current item than to copy the 0 over. So we're going to fill in the entry A of 3 comma 2 with 4, the value of the third item. Similar reasons apply when x equals 3 or 4. So here the alternative starts looking better, right? So in the row where x equals 3, the value that we'd inherit would be 2. In the row where x equals 4, the value we'd inherit would be 3. But in both of those cases, we'd prefer to have the immediate gratification of a value of 4 from the third item and just inherit the empty solution with the residual capacity. So when x equals 3 and x equals 4, we're just going to take the third item and get a value of 4. Now, good things really start happening once x equals 5, because at that point, we can both grab the third item and get its value of 4, but now we knock down the residual capacity only to 5 minus 2, which equals 3, and when you have I equal 2 and x equal 3, you actually get to a value of 2 in that case. So we're going to fill in the entry for I equals 3 and x equal 5 with 4, the value of the current item, plus 2. The optimal solution to the corresponding subproblem. It gets even better when x equals 6. We're again going to take the third item, get its value of 4. But now in the smaller subproblem, when I equals 3 and x equals 4, we actually get a value of 3. So the value here is going to be 4 plus 3, or 7. Moving to the last column when I equals 4, so here the fourth item has weight 3, so that means when x equals 0 or 1 or 2, we don't even have the option of picking it. We have no choice but to copy over the number from the column to the left, so that's going to give us a 0 and a 0 and a 4 for the first 3 rows of the final column. So now in column 3, we do have the option of picking the fourth item. That'll give us a value of 4. We also have the option of just copying over the value in the column to the left. That'll also give us a 4. So we have a tie, and in some sense it doesn't matter. So we're going to fill in the entry with a 4 when I equals 4 and x equals 3. The exact same reasoning applies when x equals 4. We're making the comparison between two things that have equal value, both equal to 4. Now, when x equals 5, we let the good times roll. We both can take the fourth item, and we get a value of 4 for the fourth item. But now when we subtract out its weight, we get a residual capacity of 2. And when x equals 2 and I equals 3, we also get a value of 4. So in this entry, we're going to write 4 plus 4, or 8. And that's superior to the alternative, which is just inheriting the 6 from the column to the left. Same story holds when x equals to 6. We can take the fourth item, get the immediate gratification of 4, get 4 from the smaller subproblem when I equals 3 and x equals 3, and that 8 beats out the alternative inheriting the 7 from the column to the left. So that completes the forward pass of the dynamic programming algorithm, filling in the table systematically using our recurrence. When it completes, of course, the optimal solution value is in the upper right corner. It's the value of the biggest subproblem. So we know at this point that the max value of any feasible solution to this knapsack instance is 8. And as we've discussed, after you've filled in the table in the forward pass, if you want to get your grubby little hands on the optimal solution itself, you can do that with a reverse pass. There's a reconstruction post-processing step. How does that work? Well, you start with the biggest subproblems, so in this case when I equals 4 and x equals 6, and then you ask, by which branch of the recurrence did we fill in this table entry? And that gives us guidance over whether to pick this item or not. So how did we get this 8? Did we inherit it from the column 1 to the left, corresponding to not taking item 4? Or did we get it from the column to the left and the subproblem with residual capacity decreased by the weight of item 4, corresponding to taking item 4? Well, if you look at it, we didn't just inherit the solution one column to the left. This does indeed correspond to taking item 4. That was the better of the two options we used to fill in this table entry. So that means that in the optimal solution, item 4 will be there. So having figured that out, we trace back through the table. We say, okay, well, let's look then at the table entry that we used to build up to this optimal solution to the big problem. So that corresponds to going one column to the left and number of columns down equal to the weight of this fourth item. That is 3 rows down. Now we ask exactly the same question. Did we inherit the solution from the previous column corresponding to picking this item, or did we use this item and build from a solution to a smaller subproblem from the previous column? Well, again, where did this 4 come from? It didn't come from immediately to the left. It came from the value of item 3 plus the optimal solution with a decreased residual capacity. And so that means that the optimal solution also includes item number 3. So what do we do then? We trace back, we go one column to the left, and we have to go now 2 rows down. 2 rows because the weight of the third item is 2. So that leads us to A of 2, 1, and at this point the residual capacity is so small that we have no choice but to inherit the numbers from the left. So we're not going to be able to pack either item 1 or item 2 into the optimal solution. So at this point, we just go left during our trace back, and then when we get to I equals 0, we're done. We know we've constructed the optimal solution, which in this case is item number 3 and item number 4. That's how you get an optimal value of 8 in this particular knapsack instance.